going to share with you today Module 5 in the short course on risk-based decision making. Module 5 has to do with risk metrics and uncertainty. Two very important topics in risk-based decision making. So the learning objectives for this module are to, number one, understand common metrics that are used in risk-based decision making. Really, these are common metrics that are different ways that risk can be expressed, and I'll talk about why that's important. And then to understand the different types of uncertainty that may impact decisions. This is a more general decision analysis point, but because uncertainty is a big part of assessing risk, it certainly plays a big role in risk-based decision making. So first, risk metrics. So what is a metric? A metric is just another word for a measurement. You might have heard it in terms of measurement and evaluation. Some people use metrics as a shorthand for measurement. So for example, if you're trying to measure length, you might use meters. If you're trying to measure weight, you might use kilograms. So it's just a way that you express the amount of something. So for risk, it's complicated because there's many different ways that risk can be measured or assessed or reported. And so choosing which one of these you use when you're doing your risk-based decision-making process is very important. So I'll walk through kind of a list of all the general metrics, but first I want to talk about how it relates to decision-making. And that's because, as we talked about in the earlier modules, a good decision is when the outcomes align with the decision-maker's preferences. So because there's so many different ways to express risk, and none of them are really right or wrong, they just contain different levels of information. So it's really important to do this work to determine which risk metric has the most meaning to the decision maker, rather than just assuming whatever risk metric you use will be right. Now the good news is that most of these risk metrics can be, you can translate from one to another with some algebra and other scientific information. But as I'll show you, there's some kinds of risk metrics that need more modeling, more analysis than others. So it's important to know up front which risk metric is going to be of interest to your decision maker so that you conduct the needed analysis. So let's go back to the risk-based decision food case study that we've been using in these modules. And this was, remember, a decision about which intervention would be selected to reduce microbial contamination. So we talked before about how effectiveness, the outcome that was identified in the paper, that's the one that's most related to this idea of risk, the impact on risk that the decision will have. Because each of these different interventions will have a different degree of effectiveness in terms of reducing the microbial contamination. So we're going to focus on developing potential risk measures that would capture this idea of effectiveness of an intervention. So think about all the ways that you could report on the effectiveness of a reduction in microbial contamination. So you have some level of contamination that you're not happy with, you want to try to reduce that risk. What are the different ways that you might report it or that you might measure it? So I'm going to go through a couple of slides with all these different ideas of metrics that could be used to represent this idea of effectiveness. So first, you could look at the amount of contamination on the product, right? So we're talking about food products, and say you have some products that have a certain level of contamination and you're trying to reduce that contamination. Well, there's still a couple of different ways that you could express it. You could say, well, what are the average level of contamination in a product? And you could say, I want to try to reduce that average level, right? That would be one way to express it. So you might express the level of contamination in terms of CFUs, and you might say we have 5 log CFUs, we want to try to get it lower. Perfectly acceptable way to express effectiveness of reduction. Or you might say, well, I really want to reduce the average rate of contamination. So I might say, well, now we have 15% of the products that have a significant amount of contamination, but I want to get that number lower. I want it to be lower than 15% of the products. Depending on what your process is, what your food is, how things are measured, these might both be reasonable expectations. Now, if you go with the average rate of contaminated products, you're going to have to be aware that you have to define what does significant amount of contamination mean, and depending on different pathogens, you might have different levels of what that means. So that's one perfectly reasonable way to express a reduction in microbial contamination. But those are about the hazard. Remember, we talked about hazard versus risk. So those really are about the amount of hazard that exists on the product. But what if we want to talk more about a risk-based kind of metric? Well, then you might talk about the public health impact, and this starts getting into people that are affected. So you might have a change in the number of people that will die. So say you have a very contaminated product, and you can estimate the number of people that are dying each year from this level of contamination, and you want to say, well, I want to reduce that number. So that would be a different kind of metric, the number of people that are not being that are not dying because of this contamination. You also might say, I care about the number of people that have severe health impacts. So in some cases you might only care about mortality, but in other cases you might care about people that have disabilities or some kind of long-term health consequences. So you want to try to reduce the number of those people. Again, a perfectly reasonable measure of risk. Or you might care about the number of people who have less severe health impacts. So maybe it's a short-lived illness, but it takes you out of work for a couple of days, but there's lots and lots of people that it's affecting. And you might say, well, I really care about reducing that number. So these are all changes to public health impact, changes in risk estimates, and none of them are wrong. It's just a matter of what the decision maker cares most about. And of course, you might care about multiple options, so you might have to use several risk metrics when you are developing your outcome consequence table. So here's a few more options. So for example, you could look at different subpopulations. So not just all people, but maybe just children. You might care about the number of children who would die or have severe health impacts or have less severe health impacts. You might also say you care about the number of women that would die or any other subpopulation, maybe a special interest subpopulation, maybe one that's more affected by foodborne illness. You could have any kind of subpopulation here, and you could measure the impact that way. And these would be all these numbers would be estimated using risk models that you would develop in the risk assessment. That's a separate short course about risk assessment. You might also talk about economic impacts, a reduction in the cost of illness with healthcare costs, productive pain, and suffering. So if you're able to reduce these illnesses, whether it's for the whole population, for children, for women, for any subpopulation, you could also express that in terms of costs. There's even a couple more options. So there's measures such as the years of life lost. So this is basically looking at mortality, but with a higher weight for younger children than for older people who die. You could also have years of life with a disability. So if it is a severe health impact that lasts for a long period of time or over your whole life, there would be a estimate associated with that in terms of how many years of life did you lose because of this disability. You could also talk about disability-adjusted life years, which is those years of life lost and the years of life with disability added together. So you might look at that as a composite measure. And finally, you might look at quality-adjusted life years, which is another way to kind of express the overall impact of the burden of this potential contamination. So all of these options are perfectly reasonable to use, and depending on what kind of data you have and what kind of modeling you did in your risk assessment, you may be able to generate these. But the point of this is really to say, when you're working with a decision maker, having that decision maker understand all of these different kinds of measures, what they represent and what they don't represent. We didn't talk about kind of regional differences. So in the United States, you might look at state level versus United States level. You could look globally versus in the country and so on. So these are all important dimensions to take into account when you're working with your decision maker to decide which risk metric you're going to use in the outcome, so that, again, you can make sure your analysis is tailored to develop that particular information. So now let's talk about uncertainty just for a little bit. Uncertainty is something that is typically present in difficult decisions. That's part of, as I mentioned a couple modules ago, it's part of why we use decision analysis, because situations are difficult when you have a lot of uncertainty in your estimates. And decision analysis provides for tools that help you address that uncertainty concretely. So there's lots of ways, lots of things that uncertainty might come from. It might come from incomplete information. It might come from a disagreement of information sources. So you might have two different studies that say different things. That's uncertainty. You might have just variability in the population, natural variability. You want to try to capture that. You might have an inability to estimate your decision. You might just have imperfect information that's available. proxies maybe that we've talked about. Or you might have uncertainty in your values and preferences. You might not really know which thing is most important to you. So these are all potential sources of uncertainty in a decision analysis. And now I'm going to talk about types of uncertainty. So when you're collecting different kinds of data, they might have uncertainty with them. And again, this is really just meant to introduce you to this idea of uncertainty. When you're conducting your risk assessment model, you're going to think about uncertainty in a specific way. And when you're setting up your consequence table, remember we had the column called weight of evidence, which really had to do with how much confidence you had in the information. If you have a large weight of evidence, you would have a lot more confidence that that information is correct. If you have, less rigorous evidence, you'd have a lower weight of evidence. So it relates to your confidence, it relates to your uncertainty, and all of these things should be taken into account when you're making the decision. So there's a few types of uncertainty. I'm just going to run through. You're probably familiar with some of them, but you might not be familiar with all of them. So these are the types of uncertainty. I'm going to go through all of these. And I wanted to mention there's a book called Uncertainty by one of my advisors, Granger Morgan, and Max Henrion, which was put out in 1990. It's a great deep look at uncertainty analysis and how it can be used to improve policy decisions. So I highly recommend that. So the most common form of uncertainty that is usually pretty much represented these days when you see analytical results is random error and statistical variation. So this is known as statistical uncertainty. It's the most studied and best understood. Really results from imperfections in the measuring object. And you can represent it in terms of standard deviation, confidence intervals, and so on. And the idea is that you could reduce this, or at least you could better understand it by taking more and more measurements. So there's always a trade-off between how much money you invest in collecting data and how much uncertainty you're willing to take. But statistical uncertainty is a pretty straightforward concept in terms of kind of narrowing down to the confidence you have in the number. Systematic error is another type of uncertainty, and that's when your measurement might be biased. The measurement tool that you're using might be biased, so it might shift everything one way or another. These kind of things are difficult to assess because you really have to understand. You can't just look at the data and see this. You have to understand how the data was generated. So there's a couple of examples that are shown here in terms of using mouse models, for example, to extrapolate to humans. That's systematic error, subjective judgment. We know that that's the case when we do it, and it's the best that we have, and so we still do it, but you have to acknowledge that there's that model uncertainty. Also, forecasting future performance based on past performance. There's a lot of good reasons to do that, but you have to acknowledge the uncertainty that it introduced. So in these cases, taking more measurements does not reduce the uncertainty. Then there's a handful of other ones that I just wanted to run through really quickly just to make sure they were clear to you. So the first is linguistic imprecision, and this has to do with using verbal categories, things like high, low, medium, like I've been doing. It's really important. A lot of studies have shown that people have different ideas of what those things mean. So when you use those kind of terms, you really need to define what you mean by high, what you mean by low, and so on. Variability I mentioned earlier. This really has to do with when you're not really looking at one quantity but a population of quantities and you're trying to figure out what the frequency distributions are. It's very common, commonly in risk assessment models represented as probability distributions. And inherent randomness, so that's when you just can't develop a model to predict it and there's just some kind of randomness that you want to kind of take that into account when you're developing your estimates. There's disagreement. There are many cases where we don't have data for things, especially in the area of food safety risk assessment. Even in Western countries, there's a lot of missing data, so we use expert opinion. So when you have experts that disagree, that's a form of uncertainty because it's not clear why they disagree, so it's part of what you need to acknowledge in your estimates. And then finally, when you just have approximations, when you use proxies and you don't have the real data for that particular element, you just have to acknowledge the uncertainty that's in that particular element. So I hope that gave you a quick introduction to understanding the common metrics that are used in risk-based decision-making, and then also understanding different types of uncertainty that you could encounter in decision-making, and some idea of how to start to represent those in your consequence tables for the decision-maker.